So here we'll talk about the force oscillation of the three simple circuits, including the RLC, the resistor, capacitor, and inductor. Okay, so this is the first one, which is the easiest one, about the resistive load. So here, considering this figure, we have a AC source. AC source. AC source. So it is specified by something like a sine wave. So it means a sinusoidal source. Okay, so it is in series with a resistor R. So this simple circuit. Okay, so we can see this is so-called the alternating EMF, because AC means alternating current. So this is so-called the alternating EMF. So so it is it can be written as E equals EM. EM is the amplitude, and then times the cosine omega d t. Omega d is the radian, the angular frequency of this AC source. Okay, so in this case, VR means this is positive, this is negative, this is ground. So VR is the voltage drop of the resistor, or the potential difference of the resistor. So VR is nothing but EM times cosine omega dt. So very trivial. So here we'll define something called a phasor, which makes it like this. So VR, and then here we have IR. So VR means the amplitude. It also includes the phase, but for this case, it is nothing but an amplitude. So VR equals IR times R. Also, it simply looks like the Ohm's law. Actually, the idea is like this. It tried to make something like the Ohm's law. So it tried to eliminate the cosine omega dt, although it is our AC source. But it tried to use the phasor to get rid of the sinusoidal there. And then this simple equation is nothing but the Ohm's law. So it tried to have R is the resistance. So, and then later on we'll call this R to be ZR, which is the impedance of the resistor. So the impedance of the resistance is R itself. So, and actually it tried to make it like VR. VR is the time domain signal, and then it equals to VR times cosine omega dt, and then IR is the time domain current. So it is VR over R, and then times cosine omega dt. So all the things are quite trivial because the resistance doesn't have any memory. So it is nothing like this. So so this is the first case, and then you can see that the voltage VR and the IR are in phase, which means the phase difference is 0 degree or 0 radian. Okay, so actually you can imagine the phasor for the phasor diagram. Suppose the initial phase is 0, so it is like we have VR and then IR, and then it is rotating, something like this. Rotating. And then actually this VR and IR are rotating, pointing to the same direction at each moment. And then how fast it rotates related to the angular frequency or angular frequency omega dt, something like this. So yeah. So this is the simplest case for the resistor. It looks like it's so stupid. Only write some trivial things. Okay, so let's come to the second case, which is the capacitive load. So here we still have an AC source, but it is in series with a capacitor rather than a resistor. So here we call this potential difference VC rather than VR. Okay, so here we have some difference. So still E equals EM times the cosine omega dt, nothing special, and then VC equals capital VC times cosine omega dt. So here VC is the phasor representation of the small vc. Small vc is the time domain. This is time domain signal. So and this is called the phase. Okay, so this is still nothing special. EM is nothing but VC, and then here IC is not VC over something times cosine anymore. So according to what we have learned before, we know that IC is C times D VC dt. So we need to take the derivative of the VCs to get the IC, and then of course multiply by C. So we can just plug in this one here. So we take the derivative of this one, then we'll have cosine. Take the derivative will be negative sine. So we have a negative sine omega dt, and then for the chain rule we have a omega d here. So we have a negative omega d, and then C here, and then VC. So take the derivative of VC multiplied by C will look like this, and then we try to put this one back to here, and then convert it back to cosine. So in high school trigonometry, you know, cosine omega dt plus or actually cosine x plus pi over 2 will be negative sine x. So yeah, I hope you still remember the trigonometry identity for this special angle. Yeah. So actually we can just put this one back to here. So cosine omega dt plus pi over 2. Pi over 2 is 90 degrees. So which is negative sine omega dt. So the point here is we still hope to have cosine here. So we make it to a phase changes, and then these two sinusoidal is with the same frequency, or same angular frequency. Okay, so we can now try to compare the difference between this one and this one. Okay, so here we'll try to define this. This is so-called the impedance of the capacitor, which is ZZ equals 1 over j omega c. So actually for the textbook, the presentation of this part is not like this. It tells you ZZ will be 1 over omega c, something like that, or negative 1 over omega c. But yeah, it's quite strange. But yeah, actually in circuit theory, we will try to consider the impedance Z to be a complex number, or for the capacitor is a purely imaginary number. So which is 1 over j omega c. You may ask why we need to come up with this j here, but yeah, I think it's a little bit hard to explain. But actually, this j is related to this pi over 2. This pi over 2. So if you still remember, we talk about the Euler's identity. Euler's identity is the exponential to I theta equals cosine theta plus I sine of theta, something like this. So actually, if we have exponential to I pi over 2, I pi over 2, cosine of pi over 2 is 0, and then sine of pi over 2 is 1. So it is nothing but I, or J. Usually I use J, but yeah, here you can write it as I, or you can write it as exponential to J pi over 2 equals J. So here you can see cosine with this one. So you can regard this one as real part of exponential to J omega dt plus pi over 2, like this. So after taking this real part, it becomes cosine of this one. So we will have this exponential J pi over 2 here, which is actually J. And here we try to consider that we have a V over I could be some sort of resistance, or generally an impedance. So we have here it corresponds to exponential to J omega dt, and then this one over this one over this one, and then we will have exponential to negative J pi over 2. So this J should be in the denominator, because 1 over J is negative J. So usually we will write it as 1 over J omega C rather than minus J omega C, although they are actually the same. So we will try to define it like this, and then we can have a simple expression as Vz equals Ic times Zc. So the point here is make it like the Ohm's law. But actually we need the definition of the impedance, and then also the phasor. So this is the phasor of the voltage across the capacitor. This is the current, the phasor of the current of the capacitor, and then this is the impedance. This is the impedance of the capacitor. So after multiplying together, it just looks like the Ohm's law, V equals IR, but here the R is generalized to be the impedance. For the impedance, in Chinese is called 阻抗. Okay. So this is actually the impedance of the capacitor, and it makes this one look like the Ohm's law. And then for the third case, which is about the inductive load. So similarly, we have this AC source, and then in series with the inductor. So in this case, still we have a E equals EM cosine omega dt. And then for the current, we actually know the current first, and then it is IL equals capital IL cosine omega dt. So still IL is the phasor of the current. And then we also know that this expression, which is VL equals L DIL dt. So we take the derivative of the current with respect to time, and then multiply by the inductor. By the inductance, and then it will be the voltage or the potential difference across the inductor. Okay, so we can try to plug in this one into here. So we take the derivative of this one. So cosine becomes a negative sign, and then for the chain rule, we also have omega d here. So it becomes negative omega d L is this L, and then IL is this IL. So after taking the derivative, the expression is like this. And then similarly, we try to plug this one into here. So it becomes a negative sign is a cosine plus pi over 2, something like this. Okay, so here still we try to make it like VL over IL. So in this case, we have plus pi over 2 phase shift rather than negative pi over 2. So in this case, we have positive J here. And then if you divide this amplitude by this amplitude, IL and IL cancel. So we have omega dL. So we have omega dL here. So it makes it like ZL equals J omega dL, which is the impedance of an inductor. Impedance of an inductor. Okay, so after making this definition, we can have VL equals IL times ZL, so which is also looking like the Ohm's law, but generalized Ohm's law. Okay, so maybe I try to get back here, so you can see for the capacitor, VC is cosine omega dt, and then IC is plus pi over 2. So you can see VC is here, IC is here. So the IC is leading by 90-degree phase shift. Yes, it's leading by 90-degree phase shift. And then for the capacitor, okay, so you can compare it here. So this is VL and this is IL, and then VL is leading, then the IL here, VC is lagging, then to the current here we have VL is leading the current by 90-degree phase shift. So this is the three special case for the RLC. Okay, so let's take a look at this sample problem, and then we can see how it is useful. Okay, so the first one is resistor R is 200 ohm, and then EM is 36 volt, FD is 60 hertz. So what is the potential difference VR, and what is the phasor VR? Okay. So here, so VR is the time domain function. So it is nothing but EM, which is 36.0, and then cosine, and then 2 pi times 60.0 times t, so which is nothing but 36.0 cosine 120 pi t, and then volt is the SI unit. Okay, so this is the time domain function. VR, small VR of t. Okay, and then it asks you the phasor VR. So VR is nothing but 36.0 volt. Which is somehow like the amplitude. Okay, so for B, what are the current IR in the resistor and the phasor IR? Okay, so here we have IRT equals VRT over R. So which is nothing but the Ohm's law. So in that case, we have 36.0 cosine 120 pi t over R is 200. Okay, so in this case it is 0.180 cosine of 120 pi t. Okay, so this is the current A. Okay, like this. So this is I out of t. And then it also asks you about the phasor I out. So the I out is nothing but 0.188. Okay. So for the resistor, it is very trivial. Okay, so the next sample problem is about capacitor. So here it says capacitor C is 15 microfarad, and the sinusoidal alternating EMF device operates at an amplitude EM to be 36 volt and frequency FD to be 60 Hertz. What is the potential difference VC across the capacitor as a function of time, and what is the phasor VC of t? Okay, so VC is actually the same as the previous case, because this is VC and then connected to here, and then the source is actually the same. So VC is of course the same expression as the previous one. So it is something like this. And then the phasor, because the time domain function is already the same thing, so VC is also the same thing. So which is nothing special here. And then we can consider the part B. What is the current of it? So actually you can just use IC of t equals C dVC dt, this case, and then you can just calculate the answer, something like what we derived in the previous pages. But actually here we can make use of the phasor. I think we can make use of the phasor. So actually IC is a VC. So here we have a capital letter, which means the phasor and the impedance. So VC over ZC. So V equals I out. So V equals IZ. So IC is VC over ZC. Something like this. Okay, so VC is 36, or we can keep it first, VC, and then CZ is 1 over J omega C. Okay, so it is nothing but J omega C VC. Okay, so now we can just plug in the number J, and then omega is 120 pi. Omega is, actually this one is the omega. So J omega C is 15 times 10 to minus 6, and then times VC is 36. Okay, so this number is J 0.203, something like this. Okay, so this is actually the phasor. And then in this case, we can simply write out the IC of t from this one. Okay, so it is the amplitude. You can just take the absolute value. So take the absolute value is nothing but 0.203. So we have a 0.203 here. And then cosine, the frequency wouldn't change. So it is 120 pi t. And then this one is J. And actually, for this one, it might be a complex number. You can just write it in the polar form. So if you write it in a polar form, it is nothing but 0.2003 exponential to j pi over 2, something like this. So you see, here we have a j pi over 2, which means that we have a we have pi over 2 here. We have pi over 2 here. Of course, this is a current. So this is it. So we can make use of the phasor. Although you feel like, oh, it is quite strange, it is a complex number or imaginary number, but the case the why we need to use the phasor is we can get rid of the derivative. Although derivative may be more familiar to you, yeah, because you have learned the calculus, but yeah, in circuit theory they try to use the phasor to calculate the so-called steady state response. For the sinusoidal input. For this case, maybe okay, you can just take the derivative and then you can find the answer. But if the circuit is much more complicated, using the phasor will make it more easy for the steady state response. If you don't use the steady state response, probably you need to write the ODE and then you try to write out the constant coefficient ODE and then try to solve for the particular solution and the homogeneous solution, and then you try to plug in the values. But here, for the steady state response, it means that we just try to ignore the homogeneous solution, because if the circuit is stable, then the homogeneous solution will tend to 0 when t is large enough. So here, for the steady state response, we only consider the sinusoidal component, because if you have sinusoidal as the input to the linear circuit, then the output will also be sinusoidal with the same frequency. The amplitude and the phase may be different, but at least the frequency will remain the same. Okay, so let's take a look at another one for the inductor. So yeah, so for part A, which is still the same, VLT equals 36.0 cosine 120 pi t, and then VL is 36.0 volt, so nothing special. And then we can just come to the part B. So for the part B, we can make use of VL equals IL times ZL. And then if you still remember, ZL is J omega L. So we have a J omega LIL, J omega LIL, and then we can plug in the number J, and then omega is 120 pi, and then L is 230 times 10 to minus third power, and then IL, okay. Okay, so actually we would like to find IL here. Sorry. Okay, so actually we would like to find IL rather than VL. So IL will be VL over J omega L. Okay, something like this. So, okay, so this one will be like this. 36.0 is VL, so this is J omega L. Okay, so in this case, this is a negative J 0.415. 0.415. Okay, so here we can actually write it as 0.415, which is the amplitude of this imaginary number, and then exponential to minus j pi over 2. So this is negative j. This is negative j. This is the amplitude, must be a non-negative number, at least 0, but usually a positive number. And this is correspond to the phase, because as you try to plot this one, this is a plus bi, so this is a, this is b, and then here for negative j 0.415, which is here, this is negative j 0.415, and then this is negative pi over 2, something like this. Okay, so this is the phasor. This is the phasor of the current. The phasor of the current. And then if we have this, we can write our IL of t as 0.415 cosine 120 pi t minus pi over 2 a, like this. So far, any questions? Okay. Okay, so here we will talk about another case, which is called the series RLC circuit. So just now we just mentioned R, L, and C individually. So here we have a sinusoidal source in series with the R, C, and L, or RLC. The order of the RLC are not so important. Yeah. So actually you need to distinguish this one with the damped oscillation. For the damped oscillation, it only has some initial power stored in the RLC, and then it will actually decay. But here for this one, we have actually an AC source here, so it will somehow oscillating. So here you can see we have a E equals Em cosine omega dt, just as before, and then we try to assume this I is the current going through this circuit, will be I, this is the phasor, will be sine omega dt minus phi, so minus a phase, so there will be a phase difference. And here it tells you that this I will be Em will be the phasor, actually the amplitude of the voltage difference across this E, so Em. And then here we have this big term in the denominator, so it is square root R squared plus blah 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 blah. Okay, so actually why it will look like this, actually you can regard it as this one R, C, and L, they are 3 components in series. So here, rather than adding them together directly, adding R plus C plus L together, we actually need to add their impedance together. So actually for the resistor, the impedance of a ZR is R, and then for this one, ZZ is 1 over J omega C. For the L, ZL is J omega L. So here, the series impedance is ZR plus ZL plus ZZ. Okay, so ZR is R, and then ZL is J omega L. So we have a J omega L. And then this one, ZZ is 1 over J omega C. So it is nothing but negative J over omega C. So here, this is negative J over omega c. So this is the total impedance for the RLC, total impedance. Okay, so now you can see why this term will look like this. Actually, this one is the amplitude of the impedance. The amplitude of the impedance. Okay, so this is a complex number. This is a complex number. This is the real part. This is the imaginary part. So the absolute value of this complex number, just say if we have a let's say z equals a plus jb, then the absolute value will be nothing but a square root of a squared plus b squared. So you just take the real part, the square of the real part plus the square of the imaginary part, and then add them together and then take the square root, will be the absolute value. So here this is r squared regarding to this one, and then this term square omega d L minus 1 over omega dc, and then quantity squared, and then take the square root. So you can see why this equation look like that. Okay, and then it also tells you that the tangent phi will be the imaginary part over the real part, tangent phi, which means that for this one, tangent phi will be b over a, because it is something like this is a, this is b, and this is a plus jb. So this phi is tangent phi is b over a, something like this. So this is the impedance. So we have the imaginary part over the real part will be the tangent of phi, and as much as it is in the denominator, so we have a negative sign here. Okay, so different from the damped oscillation, the frequency for the damped oscillation, the omega prime is omega square minus something square. I don't really remember, something like r over 2l if I remember correctly. Should be something like that. Slightly smaller than the 1 over LC square root. So this one is 1 over square root of LC. So for that one is the damped oscillation. But here we have a sinusoidal input, so the oscillation frequency will be actually the same as this one. So here this omega d referring to the largest amplitude over all frequency, because if you try to make this term the largest case, and then you try to tune out the omega d, and you need to minimize the denominator, because this is a square, so you should try to make this term 0 to make the denominator the minimum case, and then if the denominator is the minimum case, this whole term is the maximum case. So the case here is something like you try to maximize I here. In that case, you need to minimize the denominator. You need to minimize the denominator here. So you can just ignore this one. This is also a constant. So you need to minimize this one. The way to minimize this one is this one to be 0. Because if it is not 0, it is a positive or negative, then square will be a positive value. So the minimum case for this term is 0, which means that this term equals this term. And finally, omega d equals 1 over square root of LC. So that's why it looks like this. So it is so-called the resonance, 共振, resonance. Okay. Okay, so here I can try to slightly tell you why it would like that with some so-called rigorous mathematic derivation. Okay, so actually we can try to solve this one with writing the ODE governing this circuit. Okay, so or maybe we have a 10 minutes break first because it will take some time.